Howdy folks, here's another very exciting mineral analysis video. Actually, it started out as a rock identification video, but it turned out to be really boring. Just kind of a casual look-see. Showed it to be just a mica schist, and I went through a whole bunch of properties and looking at it, doing everything just kind of supported that, so it was kind of boring. So I'm going to cut all that stuff out, and now I'm left with a bunch of still boring video, but it's going to cover more of a focused topic. I did find an interesting property about this rock, and I also found some specks in here that were kind of blackish or bronzish in color, and I decided to look at that. So anyways, unless you're a real avid mineral, rock, or chemistry sort of guy, you might want to take your mouse and click elsewhere. So stay tuned. Don't fall asleep. Howdy folks, I'm back, and so are you. The next thing on the list to look at least my list, is magnetism for this rock. I have a magnet that used to be part of a hard drive on a computer drive, and they're very, very strong, so I thought that would be a good one to use. There's a paper clip. You can see it really grabs the paper clip. And here's some of the parts and pieces to our rock that we broke apart earlier, and I really don't feel anything at all. Try a couple pieces here. But I did read to suspend either the magnet or the sample. In this case, I actually suspended some pieces of this rock, and see if we could see anything that way, to see if it's a little bit more sensitive. So if I bring the magnet over, and lo and behold, it does. I don't know if you can see it very easy, but there's definitely a movement there. I'm not sure what you could see from that distance, but you know, the heavy rock definitely something in that small piece, and even in that flat piece. But so I really couldn't tell by hand, but suspended on here, it does have some magnetic attraction. Must be something in there that's magnetic, or the material is weakly magnetic. But I have a feeling that there's some of those maybe black crystals or something in there that's magnetic, causing the reaction there. So what I did do is I took a lot of the little pieces of rock, and I broke them apart. And this is actually, I got this for doing rocks and minerals. It's an agate mortar and pestle, and I made a wood handle for it because this little piece is really hard to hold and push. So now I can get a little bit more force. And it's agate because it's much harder. It sort of looks like it's marble, but it's not. Marble is actually pretty soft, so if you're doing some hard samples, you need an agate. I probably could have gotten a bigger one, but they're really expensive, and I figure I can use this to start with. But the sample was so soft, I actually used a porcelain mortar and pestle, and broke it up that way. So what I did is I actually have, this is the powder that I got. So I wanted to break it up to see if there's something inside that I can separate with the magnet and pull out of there that's the magnetic component to it. But hang on, I'm going to put you on the ring stand. You can look down on the world. And I have some of our powdered sample on some paper, and I'm going to try to separate any of the magnetic parts if there are magnetic pieces to it. So I'm going to put the magnet, and I'm using a different magnet because I needed something flat. The other one was recessed. But okay, I'll put it right on the paper, and lo and behold, you see some stuff being pulled out of there. So this is kind of a thick amount of sample, so I'm going to actually pour some off of there and spread it a little bit thinner on this piece of paper. So that's a little bit thinner. So now let's see. Okay, I got the magnet under there and it's definitely picking something up. So let me pull that off to the side, pull it around, and yeah, it looks a little different color. Looks kind of blackish. So I'm going to keep doing that. And I'm going to take a long circuitous route so all the non-magnetic stuff falls off. Okay, that bit seems to be pretty clean. So I'm going to put that in a separate container. Okay, there's the container. And we'll just sweep the magnetic bits and pieces on over. I think this is a eyeliner brush or something. As you can see, the cheapness of my lab equipment. Cut you off while I do this because this looks pretty boring. I don't know any good jokes, so it looks like this is going to take some time to get the whole thing clean. Okay folks, I completed the separation with the magnet, or at least a rough separation, because I never did get all the metallic material out of the sample. Some of it, you can still see it move, but it just wouldn't come out, at least not easily. And also, some of the material that I did get out obviously had some of the clear crystal material on it. But this is what I ended up with. The one on the left here is the magnetic material, and I did a weight of both of these containers, and it doesn't look like it, but by weight it's about 10% of the magnetic material. And once again, that's just a rough number because it's not a complete or perfect separation. So there's still some left in the original material, and some of the original material is in with the magnetic stuff. So it's probably a rough guesstimate of 10%. I just assume it's magnetite because, you know, it's attracted to the magnet and it's dark and kind of black looking. So I actually have a sample here of some small magnetite crystals, and I ground some of those up and decided to, you know, kind of compare them and just to make sure they do look alike. And they don't. I was surprised. I looked at it first of all under a microscope, and the magnetite is definitely kind of a black solid color, and this stuff that is from the rock is actually kind of iridescent, and it's not strongly, but you know, you get the light at the right angle, you'll see kind of a glint of gold, you'll see a glint of kind of a aqua color, kind of a glint of a red or a purple. So it seems to be a little bit different. Also, I found out that the magnetite is actually magnetic. So if you do use take the magnetite and put a iron nail in there, it definitely sticks to the iron nail. So it's magnetic. It's not just attracted by a magnet, but it'll actually stick to iron. So that's magnetic. While our other material from our sample, or from our rock, is definitely not magnetic. I can stick this in here and nothing sticks to it. So it is attracted by a magnet, but it's not magnetic itself. So I think they call that paramagnetic. So based on those two things, I think it's not magnetite. It's quite a different material, both in appearance and magnetic properties. I literally have 5 different videos on different methods of measuring specific gravity, and they're all boring. So I'm going to save you the drudgery of watching any of them and just tell you what I did for this mineral sample and the magnetite. Basically what I did, it was a little bit different because they were powdered. So I took about 1.5 grams of the material and put it into a volumetric flask, a very small one, and filled it up to the line and measured the weight. And basically the extra weight is the extra weight of the material above and beyond the buoyant force of the water. So based on that, you can go through some calculations and come up with the specific gravity. But there were a couple problems. I measured the specific gravity of the magnetite and came out with 4.6, while the published value is about 5.2, so that was on the light side. And what I did notice is some of the material kind of floated towards the top, so I had some air in there. So I was able to, if I shook it up, I was able to get more air out. So that's some air in the method. I need to make sure I get all the air out before and take the volume up before I measure it. The other issue too was just the smallness of the sample size. A little change in the weight made a big difference in the results. So I really need to be around a 4 to 5 gram sample size. Then I did check the specific gravity of the mineral sample, and I came up with something around 4 is what I'm guessing, based on, I had floaters. I might even be more than that because I had floaters. I also had the small sample size like I mentioned before, but in addition to that, it wasn't a perfect separation, so I have some of that lighter material that was in there. And I think the original rock, the specific gravity was down around 2.8 or something. So the other material must have been a little bit on the heavier side. So I'm guessing 4 plus or minus a pretty big range. And I don't really feel like going back through and trying to get a more accurate number. But you'll just have to take my word for it and thank me later that I'm not making you watch the video. So anyways, that's that. Let's do a streak test on this material, or both materials. I have a ceramic tile that's unglazed on the back that we can use. Unfortunately, it has all these ridges, but there's a couple of flat spots, and it's kind of dirty, but hopefully we'll see what's going on here. Bring the camera down. Okay, our sample is kind of powdered up here, so what I'm going to try to do is actually rub it on there with my finger to get in effect a streak. So I put a little bit on there. That's probably more than I need. And let's go ahead and rub it and see if I can get a streak on here. Well, I hear it kind of rubbing in. So hopefully that'll... Alright. Get the excess off there. So it looks like a blackish grayish, mostly gray, sort of streak, if that is correct. Okay, let's try the Magnetite. I have both a smaller piece here that I might be able to... Oh yeah, alright. I'm definitely getting a streak there. And I don't know if that's different or not. Maybe a little darker. I have some of the Magnetite that's powdered too. I'll try that technique. Okay. Kind of ended up being pretty close. So either black or gray on both of those, I would guess. Okay, I went back and I revisited the borax bead test now that I'm looking just at the magnetic part of the rock. And I also did a bead test with the Magnetite to see how the two compared. I finally did get a platinum wire, which does now give me a clear blank bead. And I only got 1 inch because the stuff's a little bit expensive, and I guess I'm just too cheap. But this is what it looks like. I probably should have got a longer piece, and I just put it inside a eyedropper tube, and I melted the end to hold it. So it seems to do a fine job. It's kind of soft and bends around a lot, but it should last a while. You can see some of the actual the clear blank beads that I did. So I'm getting a nice clear bead now with the platinum wire. And I did do some beads in the oxidizing flame with the magnetic material from the rock, and that's these right here, and they're definitely a, I'd call them an amber brown, yellowish brown color. But anyways, I did some with the Magnetite also, and that looks markedly different. Some of these samples up top higher up here. There's 4 of them, but the top 3 have kind of a large piece, so I ground it a little finer and did another one. And it comes out to be a light green. Definitely a different color, so it's definitely a different material. So that was kind of interesting. So I went ahead and started some of the chemical analysis, and at least getting started. This is one of the books that I'm using, is the Identification and Qualitative Chemical Analysis of Minerals. The first step is to take your sample and try to get it into solution so you can start doing chemical tests. And it's really nebulous. It's really hard to follow. They don't give any specific amounts other than the sample. He mentions 1/10 of a gram, so I started with that. And he mentions trying to use some nitric and, well, first some water, see if it's water soluble, and some nitric. But he says, you know, if that doesn't work, boil it down, add more nitric, do, you know, a whole series of stuff. And then there's a parentheses in the middle of it. Well, if it dissolved in hydrochloric, just skip and use that. So it's kind of confusing. So I did skip and tried the hydrochloric acid first, and I'm doing both the magnetite and the whatever's in the rock sample just to get a comparison. So let's go to the fume hood, and I already got started. I didn't really show you exactly what I was doing, but that's okay. But the results, hang on, the results are a lot different. I did take about 1/10 of a gram of each material and put it into a test tube, and I kind of stepwise added concentrated hydrochloric acid up to about 3 mils total here. And the rock sample actually started to turn a yellow color, while the magnetite was just kind of a light straw color. Didn't seem to do much right away. Then I started to heat it, and the rock sample actually became, looked to me like it was effervescent. It seemed to be a lot more than just a boiling of the solution. It seemed like the material was effervescent. It started to float near the top, and the magnetite didn't do that, but it did dissolve. There's still a little bit on the bottom. Looks like they came back out of solution. I think looked like I had it all dissolved, but the material here is attracted by a magnet, and what's left over here is not attracted by a magnet anymore. The reference that I'm using suggests that you filter out any residue, and I also have another semi-micro qualitative analysis book that actually uses centrifuging, and I think that might be a little bit easier, and I might be able to recover more material. So we're going to go that route. Here's the samples that were dissolved in acid. There's still some residue in there. But it looks pretty heavy, and the stuff looks clear, so I don't even know if we need to do this step, but we're going to throw them into a centrifuge, since I went ahead and bought one anyways off of eBay. But anyways, I have a centrifuge tube. These small tubes kind of get lost in the centrifuge, so I'm going to put them inside there. There's a little stop so they don't get lost down there, and I can get them back out. So there's the sample with from the rock, and this is the magnetite sample. So we're going to stick it in there, stick them both in. I can show you the inside of the centrifuge. It's looks like a 6 slot, and you want to have a balance, so 2 tubes will work, and 3 tubes will work with this one too if you make them equidistant, or 4 tubes, or 6 tubes. I guess the only combination that doesn't work is 5. So okay. We'll put the lid on, and this is a variable speed, so I really don't have any experience with this and haven't used centrifuges all that much. But anyways, we'll just put it in the middle there about maybe 2500 RPM, and we'll just spin it for a few minutes. Let's turn that baby on. The next step, what we're going to do is we're going to decant the liquid off, and eventually we're going to neutralize it with ammonium hydroxide. And when we do that, we're supposed to take the volume up to 25 mils and add a little bit more acid back to it. And that should be good. Nothing blew up, so that's good. In fact, I should probably be a little gentle. If we look at the light, it's settled down nicely. It's at an angle from the centrifuge. So we'll go ahead and decant this off with a pipette. Being careful not to get any of the solid. And what I'll do is add some deionized water and wash that. Alright, I'll put that back in the centrifuge for one more spin. And grab a fresh pipette. Aha! Got a whole bag full of them. To summarize, we have the interesting magnetic bits from that rock separated, dissolved in acid, centrifuged, pH adjusted, and then diluted. So now we're ready to analyze it. And once again, there was a whole bunch of boring video going through a whole wet chemistry analysis of every group of different metals there were. And to cut things short, we found came down to the iron group, which was kind of expected because of the magnetism. But to further explain this, let me show you a flow chart, which will make it a lot easier, because it's really confusing. Even the chart in the book is kind of hard to follow. So let me move the camera. Here's a flow chart of what I did, and it's basically the procedure in the book, Identification and Qualitative Chemical Analysis of Minerals by Orsino Smith, which you're probably getting tired of hearing about. But this is a simplified version. It gets kind of, there's one in the book, but it has all sorts of different reagents listed and specific metals. And it's a very similar procedure to the chemistry book that I have on semi-micro qualitative analysis, except the mineral book is a lot more detailed in terms of inclusive of different metals. So there's a lot more different minerals and metals in the analysis than my chemistry book. So anyways, we started with the mineral, and we dissolved it in acid, and basically any undissolved material can fall into the platinum group or a miscellaneous group of other things like silicon or tungsten. And the magnetite did dissolve, but the rock sample had some material that didn't, and that was because of the incomplete separation by the magnet. And I think with the mica we got some material that didn't dissolve out. But anyways, so we took that solution and we started the analysis, and every step involves either adding one or more reagents, bubbling something through the solution, adjusting the pH, or boiling, or a combination thereof. And what you're trying to do is precipitate a specific group of materials out at a time, and you do this in a stepwise, orderly fashion, so you know exactly what's there and how to separate it. But anyways, I don't have all the details on the steps because it's really burdensome and boring. But the first thing we did was try to precipitate out the silver group, and nothing precipitated. So we took that solution and I tried to precipitate out the rare earth group, and nothing precipitated. From there I took that solution and tried to precipitate out the zirconium group, and once again nothing precipitated there. We took the solution and didn't find any precipitate analyzing for the copper tin groups. From that we tried to get it precipitate, and actually we did. We got a nice big strong precipitate formed in both samples, and the solution was decanted off, and I tested for the calcium and sodium groups. Neither one had calcium, and the magnetite possibly had a little bit of sodium, but nothing to be significant. So anyways, this precipitate, which we got, I think, using ammonium sulfide, we did some other things with sodium hydroxide and peroxide, I believe, and we separated out the precipitate and the solution. And the solution would contain the aluminum group if it was present, but I did the analysis and didn't find anything from the aluminum group. But we definitely had a lot of precipitate in both of them from the iron group. and the iron group, which we expected because the iron group contains iron, manganese, cobalt, nickel, and indium, and some of those would definitely have magnetic properties, which we would expect. So anyways, that saves a lot of boring video, and we'll go ahead and pick up some of the more detailed video from here. Right now what we want to do is test for the iron and aluminum groups, and we're going to do that, and I guess there's two things we're supposed to do. One is add ammonium hydroxide until it's just alkaline and look for a precipitate, and I'm sure there's going to be one. And then we're going to add some ammonium sulfide to make sure all the precipitation is complete. We're all supposed to heat stuff, and I've been having trouble having things kind of explode out of the test tube, even with some boiling stones, and when you're making a precipitate you don't want anything in there anyway, so I'm using a hot water bath to heat some stuff up here today. Here's our magnetite sample, and here's the ammonium hydroxide. Like I said, I think we're going to definitely see something happen in here. Oh yeah, there's a precipitate starting already. We'll check the pH. Still a little bit on the acid side. 3 or 4 more drops. That's becoming alkaline, so I think we're good. So I'm going to set this aside. And now we'll do our magnetic part of our rock sample here. Just on the alkaline side, so that's where we want to be. Okay, we got both samples heated and centrifuged. It looks like the liquid is clear on both of them, and the filtrate is the same on both. It's kind of a blackish, maybe a very, very dark blue. And the only difference I see is on the magnetite sample, there's about twice as much. Okay, so the next thing to do is to add ammonium sulfide until it stops precipitating. Alright, this is the magnetite sample. And we'll see if we get any more precipitation. Oh yeah, we do. And I'll do our rock sample. Oh yeah, definitely a lot more precipitating out. I've added ammonium sulfide a few times here, probably more like 5 times, and we still keep getting a precipitate form. Howdy folks! Let's continue on our samples. It's been a little while since I've looked at these, but the last time we precipitated out the iron and the aluminum groups, and what I did notice is on our magnetite it's still the same. It's that really black precipitate, and on our sample, our rock sample, it was black also, but there's also a kind of a brown colored precipitate that was on there that seemed to form with time. And I did centrifuge that back down on top, so you see a kind of a different layer there, so I'm not sure what that's all about. But anyways, we're going to separate these. The solution should, if there's any, would contain the sodium and the potassium, or what are they? The sodium and the potassium groups. No, that doesn't make... No, the sodium and the calcium groups, the left side of the periodic table. The alkaline metals, alkaline earth metals, and the alkali metals. But okay, let's separate these out. Alright, there we go. We separated out the calcium and sodium groups from the aluminum and iron groups. So now what we're supposed to do is redissolve this in a little bit of acid and water and do some boiling. Okay, we dissolved the precipitate from the iron and aluminum groups in some acid and water. We boiled it, added some potassium chlorate, boiled it again. Now we're supposed to cool it down and add some sodium peroxide, which I do not have, but the chemistry book that I have uses hydrogen peroxide, so I'm going to go ahead and use that. So I'm going to add 2 mils of hydrogen peroxide to each tube. I added the hydrogen peroxide and just finishing up boiling the second sample here for a couple minutes, at which time we'll filter. Here's the result after centrifuging. Both of them have a precipitate, which indicates the iron group. There still might be some of the aluminum group in the solutions, but we definitely know that there's some of the iron group. The iron group is the precipitate on the bottom, and according to our Orsino-Smith book, we're going full circle. The next thing they do to tell what kind of metal it is from the iron group is to do a bead test. And we actually did a borax bead test on the mineral at the very beginning when we were looking at all the physical properties. Howdy folks, I'm back. I don't have anything to show you with the bead testing on the precipitate from the iron group because the beads all came out clear when they were cold. When I did them and they were hot, the beads were yellow, and after I took it out of the flame, and I took it off of the wire, and it kind of faded down to kind of a light green. And then by the time I picked them up and put them to the side and let them sit, they turned clear. So there's no point in showing you that. A bunch of clear beads. But anyways, none of the beads ended up being blue or violet or reddish that would indicate some of the other metals like manganese, cobalt, or nickel. I also did a salt to phosphorus bead along with the borax bead. And that's supposed to be yellow and turn colorless, which it did, so it matches there. Orsino-Smith also gives a number of tests in addition to the bead tests, so let's give those a try. And here's a spot plate. I haven't really used a spot plate much before. The top row is the magnetite sample. The middle row is actually just water for a blank. And the bottom row is our rock sample. So let's go ahead and put a drop of each reagent in each cell here and see what happens. It should turn blue to show us that there's ferrous iron if it's present. Let me add the potassium ferrocyanide to check for iron 3. Well, that's definitely a positive there. In the last row, we're going to add the potassium thiocyanate, and it's supposed to turn red if there's ferric iron. Yep. So, there doesn't look like there's much ferrous iron in either sample, which really is not correct because magnetite has both ferrous and ferric iron in it. So maybe we, through the myriad of testing there, oxidized all the iron into ferric form, which we must have done, because it's definitely showing a positive on the ferrous or ferric on both methods. Howdy folks, back at our samples here. Last time we did confirm the presence of iron with both the bead tests and also with some reagents which showed ferric iron but no ferrous, and I know that that's not right because magnetite definitely has ferrous iron in it. And I was looking through my semi-micro book, the chemistry book, and according to their flow chart, which is similar to the one I'm using in the Orsino-Smith's minerals book, it follows both the Fe+2 and the +3 going through the flow chart. Then at one point it's just iron 3, so I have a feeling it gets oxidized all to ferric iron, the +3 state. So when we started this, I saved the solution that we dissolved the mineral after we dissolved the mineral in acid. I'm going to go back and I'm going to actually use these solutions, and I'm going to test directly for iron Not after we went through the whole flow chart and, you know, bubbling hydrogen sulfide through it and, you know, boiling a million times and acidifying and neutralizing and all that. So we'll see if we get any different results with the testing. Same setup. The first reagent I'll add to the first column is potassium ferrocyanide, which will turn blue if we have a reaction with ferrous iron. So let's give that a try. Oh boy, this time the magnetite definitely turns blue. And how about our sample turned blue too. Now we're adding potassium ferrocyanide, and it should turn blue if there's ferric iron, which should happen with magnetite. Yep. The center water will be clear, and actually a very weak response here on our rock samples. So that's kind of what I was finally expecting, something a little bit different. So it's mostly looks like ferrous iron. So there's some minerals that would fit into that category of having ferrous iron, and that would differ from the magnetite. And we'll do a confirmation test with the potassium thiocyanate, which should turn red, which of course it will with the magnetite. And just the formality of putting it in the control, and one in the rock sample. So, well, that's interesting. So it definitely has a lot less ferric iron in our rock sample, so compared to the magnetite. It definitely shows a big difference of the state of the iron between the two samples, so that's kind of interesting. I don't know if you recall, but we had some effervescing when we first dissolved our mineral sample in the acid, and that didn't seem to happen with the magnetite. So I want to go back and check to see what the gas was giving off. Carbonates usually evolve gas with hydrochloric acid, but that's usually when they're cold, and this didn't effervesce until it was heated. So it could be giving off a hydrogen sulfide if it's a sulfide. So what we'll do is we'll go ahead and try it again. We'll heat it, and when it starts effervescing, we'll put a little piece of lead acetate paper at the top of the test tube. And if it turns dark, we'll know that there is a sulfide there. So anyways, let's go ahead and give that a shot. I do have some extra sample. Okay, here's the sample with some cold acid. It's already turning color, but we'll go ahead and heat it up. This is some lead acetate paper, and I'll moisten it with just a drop of deionized water. And it's white right now, but it'll turn a gray and darken up a little bit if there's a sulfide there. Let's go ahead and start heating this up. Already you can see it start to effervesce, I hope. I hope you can see it. Okay. We'll put this at the mouth of the test tube. Oh yeah, it's darkening up already. See how that's turning kind of grayish? Alright, well that narrows things down a lot. Okay, we're going to repeat that. This is a magnetite with acid, and we're going to heat that up. Once again, we'll check it with the lead acetate paper. Okay, it's starting to dissolve. We see some color variation and a few little bubbles coming up there too, but not much. Alright, now we're getting some bubbles, and I think that's mostly boiling, but let's see what we have. Alright, so far I see no change. Okay, as you can see, I'm boiling the snot out of the solution, and our lead acetate paper is still white, so The magnetite is not a sulfide, which we already know, but we just wanted to confirm with the comparison test there. So that's really interesting too. So our mineral sample is a sulfide. Okay, enough of beating this mineral up in the lab. Let's see what we have. We should have enough information by now. If you're not seeing it already, I made a chart with a bunch of different iron minerals and their properties and compare it to what we found out during this long analysis in the lab. Some of them are oxides, but most of the oxides and the hydroxides have a lot of ferric iron in them, which our sample did not have. Also, some of the oxides are pretty heavy, like the magnetite and the hematite have pretty high specific gravities. We found out that ours was a little bit lower than that. Also, we noticed that there was a gas evolved when it was heated. And there's only a couple minerals that do that. One of them was a carbonate, but when we measured the gas that was evolved, it was a sulfide and not a carbonate. So that was siderite. So I think we can eliminate that one. It also has a different streak and color and everything else. Then there were some other sulfides in there. Like pyrite and marcasite, but those again, the specific gravities were a little bit heavier, and also they're not magnetic, which ours was, and the magnetic stuff seemed to be a big clue. So based on our whole list of things that we analyzed, one, that we found that it was mostly ferrous iron, maybe a little bit of ferric, that the color was kind of a dark, either bronze or blackish color. It had a black or grayish streak. The specific gravity was 4 plus or minus. Like I explained, that was really kind of an estimate. It was magnetic. It dissolves in hydrochloric acid. A gas is evolved, and the gas is hydrogen sulfide. So based on all those items, the mineral that fits, now the drum roll, it's pyrrhotite. And I'm really happy with the results, because a lot of times you go through this big analysis or study on something and it comes out to be a bit of a question mark. But this fits so well that I feel real comfortable in having analyzed this sample. So I thought it was something else. I thought it was the magnetite, but that proved to be wrong. And but we did find out what it was, so that was kind of cool. So if you're still awake and you're still sober after watching this video, you deserve an award. That's for sure. I think I mentioned before, I have a bunch of buckets full of rocks and minerals that I'll be going through at least some of those. So hopefully I can get another video out about that, and it won't take me, hopefully not as long, to analyze one of those as it did for this one, because this one I went step by step and looked at everything. So I have a little better feel for what to do and some steps that I might be able to skip. So anyways, thanks for watching the video. I had a lot of fun, and stay tuned for the next one.